We are living in a universe that is full of bright objects. To the unaided human eye, the night sky is resplendent with over 9,000 individual points of light, but that perspective covers only a bare fraction of the universe. The nearest visible star system is Alpha Centauri, which is about 4.25 light-years away. The closest star in this three-star system is Proxima Centauri, but because it's a red dwarf, it's too dim to be seen without a telescope. The farthest star that's visible to the naked eye is V762 Cas, a variable star sitting a whopping 16,000 light-years away. Although it is likely 100,000 times more luminous than the Sun, that incredible distance means it hovers right on the edge of typical human night vision in ideal conditions. All of the stars we can see without a telescope are much more massive than the Sun. Stars like the Sun and smaller are too dim to overcome the light years of distance between them and us, rendering them invisible. Without the volume contained by the distance to V762 Cas, there are about 9,000 visible stars and over 1 million invisible ones. But while V762 Cas is the most distant star we can see with the naked eye, it's not the farthest thing we can see without a telescope. That honor goes to the Andromeda Galaxy. Containing upward of 1 trillion stars, it appears to us as a fuzzy patch about the size of an outstretched fist. When you look at Andromeda, you're receiving light that first began its journey over 2.5 million years ago. Some flashes and explosions soar to incredible levels of brightness, making them temporarily visible even at extreme distances. For example, in 2008, the gamma-ray burst GRB080319b was visible to the naked eye for about 30 seconds, despite going off over 7.5 billion light-years away. That means that when the light of this gamma-ray burst first began its journey, our solar system hadn't even formed yet. When Galileo perfected the astronomical telescope in the early 1600s, the universe opened up before us. Telescopes allow us to see dimmer objects because they can collect more light and more distant objects because they also magnify images. Still, even with our most advanced ground and space-based telescopes and most comprehensive surveys, we have managed to map less than 3% of all the stars in the Milky Way galaxy and less than 1% of the galaxies in the observable universe. The most distant galaxies are still inaccessible to us. They are simply too dim and too small for us to detect. Thus, for years, scientists have been bugged by questions of how monstrous galaxies, gigantic solar systems, stars, and planets came into being. Sure, there are many theories that have been developed and many even verified through various indirect evidences, but none can be confirmed. Confirmed? An odd choice of a word indeed, because the only way it could ever be confirmed would be if we could go back in time and watch it all happen from scratch. Inching towards science fiction now, aren't we? But the James Webb Space Telescope is such an enigma that falls in the twilight zone where science fiction and reality meet. Without traveling so much as even a fraction of a second back in time, the $10 billion instrument is looking at galactic events that happened millions of years ago. And in an extraordinary effort to lift the veil on the universe's secrets, the powerful sharp eyes of James Webb has captured the most distant star ever detected, within the first billion years after the Big Bang. Webb's near-infrared camera instrument reveals the star to be a massive B-type star, more than twice as hot as our Sun, and about 1 million times more luminous. With this awe-inspiring discovery, James Webb could fill in long-standing gaps in our knowledge, allowing us to finally see exactly how the universe transitioned from a formless expanse of churning plasma into the familiar arrangements of galaxies, stars, and planets that grace the sky. The star taken by James Webb has a technical designation WHL0137LS. But scientists prefer to call it by a much catchier name, Earendel. Fans of the author John Ronald Reuel Tolkien famous for fantasy novels including the Lord of the Rings series and the Silmarillion, might already find this name familiar. And as NASA astronomer Michelle Thaler confirmed, the name is truly inspired by Tolkien's fantasy writing. In Old English, Arundel is a personal name, but it also can mean the morning star or the dawn. In The Lord of the Rings, Arundel is a half-elven character who travels the seas carrying a jewel, a Silmaril, called the Morning Star. According to Thaler, WHL0137 LS is the first star, the farthest star we've ever seen. So, Arundel is a beautiful name for it. Arundel was first discovered by the Hubble Space Telescope in 2022. It has taken 12.9 billion years for Arundel's light to reach Earth, meaning the star was shining less than a billion years after the Big Bang spurred our universe into existence. However, Arundel doesn't lie a mere 12.9 billion light-years away from us. Because the universe has been expanding at an accelerating rate since the Big Bang, the star now lives a whopping 28 billion light-years from Earth. Given the vast distance, even a star as brilliant as Arundel would be impossible to see from Earth. The star is located in the Sunrise Arc galaxy and is detectable only due to the combined power of human technology and nature via an effect called gravitational lensing. Both Hubble and Webb were able to detect Arundel due to its lucky alignment behind a wrinkle in space-time created by the massive galaxy cluster WHL013708. The galaxy cluster, located between us and Arundel, is so massive that it warps the fabric of space itself, which produces a magnifying effect, allowing astronomers to look through the cluster like a magnifying glass. While other features in the galaxy appear multiple times due to the gravitational lensing, Arundel only appears as a single point of light, even in Webb's high-resolution infrared imaging. Based on this, astronomers determine the object is magnified by a factor of at least 4,000, and thus is extremely small, the most distant star ever detected, observed 1 billion years after the Big Bang. The previous record holder for the most distant star was detected by Hubble and observed around 4 billion years after the Big Bang. Another research team using Webb recently identified a gravitationally lensed star they nicknamed Quilor, a red giant star observed 3 billion years after the Big Bang. Stars as massive as Arundel often have companions. Astronomers did not expect Webb to reveal any companions of Arundel since they would be so close together and indistinguishable on the sky. However, based solely on the colors of Arundel, astronomers think they see hints of a cooler, redder companion star. This light has been stretched by the expansion of the universe to wavelengths longer than Hubble's instruments can detect, and so was only detectable with Webb. Webb's near-infrared camera also shows other notable details in the Sunrise Arc, which is the most highly magnified galaxy yet detected in the universe's first billion years. Features include both young star-forming regions and older established star clusters as small as 10 light-years across. On either side of the wrinkle of maximum magnification, which runs right through Arundel, these features are mirrored by the distortion of the gravitational lens. The region forming stars appears elongated and is estimated to be less than 5 million years old. Smaller dots on either side of Arundel are two images of one older, more established star cluster, estimated to be at least 10 million years old. Astronomers determined this star cluster is gravitationally bound and likely to persist until the present day. This shows us how the globular clusters in our own Milky Way might have looked when they formed 13 billion years ago. Astronomers are currently analyzing data from Webb's near-infrared spectrograph instrument observations of the Sunrise Arc galaxy and Arundel, which will provide precise composition and distance measurements for the galaxy. Since Hubble's discovery of Arundel, Webb has detected other very distant stars using this technique, though none quite as far as Arundel. The discoveries have opened a new realm of the universe to stellar physics. and new subject matter to scientists studying the early universe, where once galaxies were the smallest detectable cosmic objects. The research team has cautious hope that this could be a step toward the eventual detection of one of the very first generation of stars, composed only of the raw ingredients of the universe created in the Big Bang: hydrogen and helium. Interestingly, not only focused on distant stars, James Webb also discovered and characterized galaxies found in these very, very early stages of our cosmic history. Less than 1 year after James Webb began science operations, we have over 100 galaxy candidates that take us back to the first 400 million years of the universe, and several of them have already been confirmed to indeed be ultra-early and ultra-distant. And instead of GNZ11, the galaxy JADES GSZ13-0 is the name of the current record holder. This galaxy is a high redshift Lyman break galaxy discovered by the Webb Telescope during NIRCam imaging for the JADES on 29 September 2022. Spectroscopic observations by James Webb's NIRSpec instrument in October 2022 confirmed the galaxy's redshift of Z equals 13.2 to a high accuracy, establishing it as the oldest and most distant spectroscopically confirmed galaxy known as of 2023, with a light travel distance of 13.4 billion years. Due to the expansion of the universe, its present proper distance is approximately 33 billion light-years. And not only the first one, but the second and fourth most distant galaxies ever seen also have been spotted by the eagle eye of James Webb. The discovery was made possible thanks to a huge helping hand from a massive gravitational lens in the form of the galaxy cluster known as Abell 2744, nicknamed Pandora's Cluster, which is located about 3.5 billion light-years away from us. The immense gravity of the cluster warps the very fabric of space-time sufficiently to magnify the light of more faraway galaxies. One, designated Uncover ZN13, has a redshift of 13.079, confirming it to be the second most distant galaxy known. We see Uncover ZN13 as it existed just 330 million years after the Big Bang. The other galaxy recently discovered, Uncover Z12, has a redshift of 12.393, placing it in fourth place in the all-time list of most distant galaxies. We see this realm as it was just 350 million years after the Big Bang. What marks the two Uncover galaxies out as different is their appearance. Other galaxies seen at similarly high redshifts seem to be point-like, indicating they are very small, just a few hundreds of light-years across. But one of ours appears elongated, almost like a peanut, and the other looks like a fluffy ball. On the other hand, the Uncover galaxies, on the other hand, have structure. These galaxies are also bigger, with Uncover Z12 sporting an edge-on disk about 2,000 light-years across, which is 6 times larger than other galaxies seen in this era. Although the dichotomy in galaxy properties, even at this early stage in the universe, is eye-opening. Both of the newfound realms have general characteristics that are strongly supportive of the Big Bang model. This model describes how, in the aftermath of our universe's creation, galaxies began life small before growing rapidly through mergers with other galaxies and gas clouds. This growth, in turn, spurred more star formation, which ultimately increased the abundance and variety of elements contained within the young galaxies, introducing substances to them that are heavier than hydrogen and helium. The galaxies uncovered by Uncover, if you'll pardon the pun, are young, small, have a low abundance of heavy elements, and are actively forming stars, all of which supports the whole paradigm of the Big Bang theory. And most recently, James Webb has made detailed observations of the galaxy, dubbed GZ9P3, which is seen as it was just 510 million years after the Big Bang. That's during the relative infancy of the universe, which is now 13.8 billion years old. The research team discovered that, much like other early galaxies seen by James Webb, GZ9P3 is far more massive and mature than expected for a galaxy in the infant universe. During the ancient time period in which it's been spotted, it already appears to contain several billion stars. When it comes to the cosmic conundrum of how early galaxies grew to become so massive so quickly, GZ9P3 could be a real puzzle. Not only is it more massive than expected, but it is around 10 times more massive than other galaxies James Webb has seen in similar eras of the universe's history. As Kit Boyette, team member and a scientist at the University of Melbourne, wrote for the Institute's Pursuit publication, just a couple of years ago, GZ9P3 appeared as a single point of light through the Hubble Space Telescope. But by using the James Webb Space Telescope, we could observe this object as it was 510 million years after the Big Bang, around 13 billion years ago. GZ9P3 is simply remarkable. Besides its size and maturity, its shape also reveals clues to its creation. Using James Webb and direct imaging, the team was able to determine that GZ9P3 has a complex shape with two bright patches that reveal its two dense nuclei. That indicates GZ9P3 was likely created when two early galaxies smashed together in the infant universe. This collision may have still been ongoing during the time at which astronomers noticed GZ9P3 with the Webb telescope. As Boyette explained, the James Webb imaging of the galaxy shows a morphology typically associated with two interacting galaxies, and the merger hasn't finished because we still see two components. When two massive objects join like this, they effectively throw away some of the matter in the process. So, this discarded matter suggests what we observed is one of the most distant mergers ever seen. In addition to determining the age, mass, and shape of this ancient galaxy, Boyette and colleagues were able to probe deeper within GZ9P3 to examine the stellar population of these colliding galaxies. Because young stars are brighter than their older counterparts, they usually dominate galaxy images, especially those that are so distant their light has been traveling to Earth for billions of years. For example, a young, bright population sparked by the galaxy merger, less than a few million years old, outshines an older population already over 100 million years old. The glass collaboration worked around this by taking spectroscopic observations of GZ9P3, as well as by tapping into direct imaging. Spectroscopy can be used to determine the elements that make up stars. Because young and old stars have different compositions, this allowed the researchers to separate the two categories in this early galaxy. Older stars have worked their way through the hydrogen supply in their cores, having already fused it all into helium, and then fusing this helium to create even heavier elements, which astronomers call metals. This means older stars are richer in metals than younger stars, which are still dominated by hydrogen and some helium. The study team used James Webb to detect specific elements in the older star population of GZ9P3. These target elements included silicon, carbon, and iron, the latter of which is the heaviest element that can be synthesized by stars. This means these stars, when they died in supernova explosions, would have enriched the early universe with metals. Much of this metal content would have gone on to become the building blocks of the next generation of stars. In addition, the team discovered that the population of old stars in GZ9P3 was much larger than previously suspected. This means that, while astronomers have been aware of this cycle of stellar life and death, and the increasing metal enrichment of subsequent generations of stars, the GZ9P3 observations indicate galaxies may have become chemically mature faster than had been suspected previously. These observations provide evidence of a rapid, efficient buildup of stars and metals in the immediate aftermath of the Big Bang, tied to ongoing galaxy mergers, demonstrating that massive galaxies with several billion stars existed earlier than expected. In another groundbreaking observation, James Webb has gotten the first ever look at the light of ancient stars shining around some of the biggest, brightest, and oldest black holes in the universe. Quasars, galactic cores containing active supermassive black holes, are among the most ancient things in the universe. As dust and gas accelerate toward the quasar's central black hole, the quasar emits such bright radiation, typically 1,000 times brighter than the entire Milky Way, that astronomers have a hard time observing the fainter light of stars in the quasar's galaxy. This makes it challenging to study the galaxy's shape and mass. But for the first time, researchers at MIT have managed to unpick this mixture of signals and detect the faint stellar light from stars and galaxies around some of the oldest quasars in the universe. Their results, published May 6th in the Astrophysical Journal, reveal that, relative to their host galaxies, these ancient supermassive black holes are around 100 times bigger than their counterparts in the nearby universe. These results were possible thanks to James Webb's superior sharpness and resolution. Over 120 hours of telescope time, the team observed 6 quasars, all estimated to be around 13 billion years old, some of the oldest objects in the universe. As lead study author Minghao Yue, a postdoctoral scholar at MIT, said in a statement, "The quasar outshines its host galaxy by orders of magnitude, and previous images were not sharp enough to distinguish what the host galaxy with all its stars looks like." Using the improved data from James Webb, the team managed to untangle the signals in these ancient galaxies by modeling which light appeared to be coming from a point source, the quasar, and which light seemed to be originating from a more diffuse source, the surrounding stars. With the relative brightnesses in hand, the team then estimated the masses of each quasar and its host galaxy. They calculated that the average mass ratio of quasar to galaxy was 1:10, compared with 1/1000 for younger supermassive black holes in the nearby universe. But the explanation for why these ancient black holes are so massive isn't immediately apparent. A standard black hole forms when a star runs out of fuel and undergoes gravitational collapse, triggering a supernova. The resulting black hole then gradually consumes material throughout its lifetime, growing over time. As study co-author Anna Christina Eilers, an assistant professor of physics at MIT, said in the statement, "These black holes are billions of times more massive than the Sun. At a time when the universe is still in its infancy, black holes in the early universe seem to be growing faster than their host galaxies." According to the standard pathway for black hole formation, these black holes simply shouldn't have had enough time to get as big as they are, raising the possibility of alternative formation methods. One proposed mechanism is direct collapse. In this model, instead of a star collapsing to generate a black hole, a giant cloud of dust and gas collapses, bypassing the star stage completely. In theory, this could generate much larger black holes, known as direct collapse black holes, giving them an evolutionary head start to become supermassive earlier than conventionally possible. Although it's still a theory, in 2023, astronomers announced the first candidate for a galaxy containing a direct collapse black hole. Although the origins of these unexpectedly large black holes is still unknown, this work gives scientists insight into the development of these galaxies and quasars in the early universe. In another remarkable discovery, James Webb Space Telescope focused its sharp eyes on the most distant and oldest black hole ever seen. The discovery could be a massive step forward in understanding how supermassive black holes reached masses equivalent to millions of billions of times that of the Sun in the very early epochs of the universe. The black hole dwells in the ancient galaxy GN11, which is 30.4 billion light-years away, and is thus seen as it was just 400 million years after the Big Bang. The black hole itself is around 6 million times as massive as the Sun and seems to be feeding on matter from its surrounding galaxy 5 times more rapidly than the limit suggested is sustainable by current theories. University of Cambridge Department of Physics and team leader Roberto Maiolino described the discovery as a giant leap forward for black hole science in a statement. The size of early supermassive black holes that formed when the universe was less than 1 billion years old is a problem for formation theories, because reaching a mass of millions or billions of times that of the sun should take billions of years of constant feeding. As Maynooth University research fellow John Reagan, who was not involved in this research, said in reference into previous discovery, "It's like seeing a family walking down the street, and they have 2 6-foot teenagers, but they also have with them a 6-foot-tall toddler. That's a bit of a problem. How did the toddler get so tall? And it's the same for supermassive black holes in the universe. How did they get so massive so quickly?" Scientists currently have 2 main routes that black holes could take to reach supermassive status in the early universe. They could start out as small black hole seeds that are created when massive stars collapse at the end of their lives and after millions or billions of years, or they could skip this stage entirely. This could possibly occur if vast clouds of cold gas and dust collapse to immediately form a heavy black hole seed with a mass a few million times that of the sun. That way, the process gets to fast forward through millions or billions of years of stellar evolution, getting a head start on the feeding and merger processes that help black hole seeds grow to supermassive black holes. The discovery of this new ancient black hole with a mass a few million times that of the sun favors that heavy seed theory. But on the flip side of this, the rate at which the black hole in GN-ZL11 is accreting matter could suggest that black holes may be capable of feeding much faster than other black holes discovered in the early universe have been observed to do so. This would be a leg up for small black hole seed theories. A mathematical formula known as the Eddington limit marks how fast a body, like a star, can accumulate mass without the radiation it emits, its luminosity, pushing that mass away and thus cutting off that food supply. While black holes don't emit light because they are bounded by a light-trapping boundary called an event horizon, their massive gravitational influence does cause the material that swirls around them to be violently churned and heated, emitting radiation in the process. The more rapidly a black hole feeds, the more intense the light from that region, called an active galactic nucleus, is. Thus, the Eddington limit applies to this region, and it can similarly act to push material away and cut off a black hole's feeding frenzy. This newly discovered black hole is accreting matter from its host galaxy at a rate 5 times higher than the Eddington limit. Periods of so-called super-Eddington accretion can occur but do so in limited bouts. The team estimated that if this period of voracious feeding for this black hole had been proceeding for 100 million years, it might not have had to start life as a heavy black hole seed. It could have formed from a much lighter stellar mass black hole seed between around 250 million and 370 million years after the Big Bang, and rapidly grown to the mass it is, as James Webb observes it, 13.4 million years ago. One thing the team is fairly certain of is the intense feeding of this black hole is responsible for GN-Z11 itself, which is around 100 times smaller than the Milky Way and highly luminous. But the gluttonous black hole is also likely to stunt the growth of its host galaxy. Ultra-fast winds of particles belched out from around the feeding black hole are likely to be pushing away gas and dust from the galaxy's heart. Cold clouds of gas and dust collapse to birth stars, so this means that the black hole is grinding stellar birth to a halt, in the process killing the growth of this small galaxy. As well as learning more about this black hole and its galaxy, the team behind this research believes that the power of James Webb should help uncover more black holes in the early universe. In particular, they are aiming to discover small black hole seeds in the infancy of the cosmos and put to bed the debate surrounding the premature growth of supermassive black holes. As Maiolino concluded, it's a new era. The giant leap in sensitivity, especially in the infrared, is like upgrading from Galileo's telescope to a modern telescope overnight. Before the James Webb Space Telescope came online, I thought maybe the universe isn't so interesting when you go beyond what we could see with the Hubble Space Telescope. But that hasn't been the case at all. The universe has been quite generous in what it's showing us, and this is just the beginning. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.